Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, now we just learn the last topic in our fluid mechanics. Okay, the last topic is dimensional analysis and similitude. Okay, the last topic. Okay, so at the end of this chapter, students should be able to make the use of the study of dimension for better understanding of flow phenomena, and then understand the law of similitude, prediction of the performance of a prototype based on tests carried out on models. Okay, so introduction for dimensional analysis. Okay, actually this DA is one approach to solve fluid mechanics problems is used by using dimensional analysis, okay, or mathematical techniques, okay, that used to study the dimensions. Okay, dimensional analysis or DA is related to similitude. However, the approach is different. Okay, dimensional analysis, okay, is a technique to reduce the number of variables to be studied in an experimental investigation of a physical phenomenon. In DA, to understand the fluid phenomena, we need to predict the physical parameters that will influence the flow, then group these parameters into dimensional combination. Okay, so in DA we just use the unit only. Okay, so all physical phenomena are expressible in terms of a set of basic or fundamental dimensions. So in dimension here we learn the mass in symbol of m, length is L, time is a T, and temperature is theta here. Okay, so in SI unit, so we know that the unit for mass is kg, kilogram, length is using the meter, okay, and time is using the second, and the temperature is using the degree Celsius. Okay, based on the US unit, so we just use the mass is using the pound, the length is feet, and the time also the second, and the temperature is using the degree Fahrenheit. Okay, so all equation related to a physical phenomenon must be dimensionally homogeneous. So this is known as a principle of dimensional homogeneity. So they have two systems in the okay, so we use the SI unit. Okay, so we use the SI unit based on the mass, length, times, and theta here. So we use using the SI unit. This is SI unit. Okay, this is the US unit. Okay, so we learn this SI unit. Okay, so now, so dA is the n equation which express the proper relationship between the variables in a physical phenomenon will be dimensionally homogeneous. So this means that each of additive terms in an equation should have the same dimension. So example here, so to get the pressure, we know that we have learned that the pressure is equal to density times by the G and times by the H. Okay, so the unit is kg per meter second. Okay, so in pressure using the kg per meter second, and also the unit here is density times by the G and times by the H is also the kg per meter second. So this unit, so that we learn in this topic 6, okay, based on the dimensional analysis. Okay, so now we look at the area of rectangular. So we know that the rectangular is based on this. This is length. Okay, so this is length here, and this is the B, width. Okay, so the length times by the width here, so we get the area. Okay, L times by the B. So but in DA, so value is not important, so we just only use the unit. Okay, so the unit of length and the width is length L, and the width is also L. Okay, so we use the L times by the L, so we get the L2 here. Okay, so the area, so we get the area is equal to L2. Okay, because the unit of area is meter squared. Okay, so to get the value of volume here, So we know that the volume, okay, the unit is meter cubic. Okay, so that's we use the letter L, sorry, L power of 3. Okay, so based on this is based on the unit. Okay, the unit in dA, so this is called the dimensional analysis unit. Okay, so we use that unit only. Okay, so we know that the velocity here is the length divided by the time here, so meter per second. So this is the unit of velocity is meter per second. So we convert to use this dA, so this is called the dA. So we use the unit here. Okay, the unit in dA is mass. Okay, meter is length. Okay, second is the time. Okay, so the length times by the times power of 1. Okay, actually this is also can use as length divided by t. Okay, so we can get here. Okay, and the force is mass times by the acceleration. So the unit is kg per meter second squared here. Okay, so we just convert to dA here. M is the mass kg. Okay, and the L T, okay, squared here. So kg per meter squared. Okay, kg per meter squared here. So the mass times by the acceleration. Okay, based on the unit here. Okay, so all we just use the table here. Okay, actually they have the table also for this. Okay, for this dA here. So we know that the time, length, mass, force, area here, and velocity here, and acceleration here. Okay, and momentum. So this the unit for SI unit. So this is SI unit. This is US unit. Okay, so we just use the MLT here. Okay, MLT theta. Actually, they have the theta. Okay, theta is for the angle. Okay, so we use this system for dimensional analysis. Okay, so significance of dA. Okay, actually the significance of dA is useful for research study. Okay, especially in design by reducing number of variable. Okay, first to express in dimensional equation to show the significance of each parameter. Okay, to simplify the analysis of complex phenomenon in systematic order. Okay, so this is the dA. The method, there are a lot of methods such as Bridgman method, metric tunnel, etc. But the most popular are Rayleigh method. So we use the Rayleigh method and also the theorem pi Buckingham. Okay, so this method. Okay, now we look at the first method, Rayleigh method. Okay, so a basic method to dimensional analysis method can be simplified to dimensionless groups controlling the phenomenon. Okay, so flow chart on your right shows the procedure. So this is the procedure here. First, you must know that write the functional relationship in the form Y here. Okay, Ka power of P, B is power of Q, C is power of R, and the D type power of S. Okay, and then determine the net power of each of the three dimensions in terms of P, Q, R, and S. Okay, so apply the principle of dimensional homogeneity and solve the simultaneous equation. Okay, so this is the procedure to find the Rayleigh method. Okay, so first you look here. Okay, express dimensional equation for the speed v with a pressure wave travel through a fluid. Okay, consider the physical factors probably influence the speed. Okay, compressibility, E or K is density, and kinematic viscosity. So the parameter that include in this question is speed. Okay, the E or OK, we use just K, or use the density and also the kinematic viscosity. So this is include the V, okay, speed, the K, the density, and also the viscosity. So they have the 1, 2, 3, 4. They have 1, 2, 3, 4. 4 variables. Okay, so 4 variables in this question. Okay, so we write the equation like this. So write the equation like V, the speed, is equal to C is the constant. Okay, the constant for dimensional constant. Okay, k is the compressibility. They use K, and the density and the viscosity. So we just put the power here. Okay, the power of K, B, and D. Okay, so A, B, and D. So you can also whatever symbol that you can use, or maybe you can use that is M, N, O. Okay, and so on. Okay, in this case I use the A, B, and D. Okay, so then insert fundamental dimension into the equation while C is dimensional constant. So we just put the dimension of speed here. Okay, the speed is L over T, so just put here L over T. C is constant, is actually as the one here, C, and the K is based on MLT squared here. Okay, and just put the A here and the K for here, and the speed here, and the density is here. So you get put the B here and the kinetic viscosity here and the D here. Okay, so you write the equation and insert the fundamental dimension. Then you satisfy dimensional homogeneity. Exponent of each dimension must be identical on both sides of this equation. So you put here. Okay, so based on this L over T, based on the L, okay, L over T, this is velocity, based on the here M over LT squared here. So you just put the A, and then M over L2, L3, okay, B, so you get the B here, and and L2T, and L2T, power of T. Okay, so you just put the for M here. Okay, they just only have M, L, and T. So you put for M, L, and T. So this is based on, this is the right side. Okay, this is based on the right. Okay, so this is for left side here, based on the left side here. Okay, and this is based on this term here. Okay, so you look at the M. So for M, for this here, okay, then no M here. So if no M, so we just put M is 0. Okay, so L, so they have the L here, they have 1L. So 1L is 1 here. Okay, and the T is at the bottom here, so they have the -1 here. Okay, so that's why we just put the -1 here. Okay, so this is based on the left side here, and then this is look at the right side here. Okay, at the A here, okay, at the M. Okay, so you look at the M, they have the A. Okay, so that's the 1A. So 1A, and also at the B here, they have the A and the B. So you have the B, and you just put the A plus the B. Okay, there's no M at the D here. Okay, so now we look at the L. Okay, so at the L here, so at the A here, they have the L. So they have the -A. So you get the -A because this is -1 times by the A. So that's why you get the -A. And at this here has the -3b, so you get the -3b. Okay, and this is the L here, there's 2d, so that's plus 2d here, so you get the 2d. And then look at the T here, so the T here, there's a -2a, so that's you get the -2a. And there's no T here at the B, and the T at the D here is -1, so you get the -1. Okay, and then you solve these equations from this one. So you solve this equation, you get the A is equal to -b. Okay, so you get the -b, and then you solve this. Okay, as the D is equal to, okay, D is equal to -2a. Okay, -2a, so you plus 1. Okay, so you get the D here. Okay, so the B So you just put the A as the B here, okay? So you put the A in this B here, okay? So you get the -2 negative B, okay, plus 1, okay? So you get the negative, 2B plus 1, okay? So maybe you can get the B, okay? So you get the D, okay? So you get the A is negative B, okay? So the A, you just put the D here, okay? And just, okay, sorry, you just solve back again, okay? Okay, so you get the, okay, so you get the D is equal to negative 2A plus 1, okay? So you get this, okay? So you get this is as the 1, okay? So you get as the, this is just, okay? Okay, you just get the first here, second here is you get the A and B, D, okay? So D you get the, this is as the 2, okay? So you just put the A and the 1 here and the 2 here in this B here. So you get the, this is the, so we get the A is equal to negative B plus 2D. Okay, so A plus 2D minus 1. Okay, so you just put the B as the B here. Okay, so you get the A. So you just put the A in the B here. Okay, so the A. So you put the 1 and 2 is in this third. Okay, and then you solve here is solve to by substituting, okay, 1 and 3 in 2. Okay, so you just substitute, so you until you get the value here. Okay, so you solve the A here, so you get the 3B here. So A is B here, okay? So you get the 2, actually the A, okay, is equal to negative 3B plus 2D minus 1. Just put the A is negative B. So you get negative 3B plus 2D and minus 1. Okay. So you just put the D is also to A here. So you just put the A here. Okay. So B, sorry, we're just using the S, the A. Okay. So the D here, so the A. Okay. So the A negative 3 by the B is negative A, okay, plus 2D is negative 2A plus 1, okay, so you get the value of A, okay, until you get the value of A, and then you get the B, and then you get the D, okay, so you get the A is 1/2, B is negative 1/2, and D is you get the 0. Okay. Try to solve again based on this calculation here. Try to get the A, B, and D. So now after you get the A, B, and D, so you just put again in this formula. Okay, you just put the V is equal to constant C, K is power of A, density is power of B, and the viscosity power of D. So you just put the A, B, and D here. So you just based on the C here. Okay, from this, okay, you just control here based to this here. Okay, so you get the C, K, and the P here. Okay, and the V1 is 0. Okay, so wave speed is not affected by the fluid kinematic viscosity. Okay, so they just affect by the K, compressibility, and the density. Okay, so we get this formula because you must express the parameter until you get the formula here. Okay, so now look at the example here. Okay, so the drag force on a sphere in laminar flow is known to depend on its diameter d, velocity of flow v, density of fluid, and coefficient of viscosity. So obtain an expression for using Rayleigh method. So using the Rayleigh method, so the parameter that in this question is the drag force. So the drag force parameter, that's also the diameter. Okay, so is also the parameter is the diameter. Okay, and the velocity, and also the coefficient of viscosity. So the viscosity. Okay, so using the Rayleigh method, so that 1 2 3 4 4 1 2 3 4, sorry, the diameter, velocity, density. So also the density, they have the density and the viscosity. So they have 4, they have 5. So they have 1 2 3 4 and 5. Okay, so this is using the force. Okay, force, drag force here is okay. Okay, actually to using this is using the FLT, instead of using the US unit. So you try to use the SI unit, so we can put here as the drag force is function of C, okay, D of A, velocity of B, density of C here, and the viscosity of D. Okay, this is the constant coefficient. Okay, so we just put as the 1. Okay, so they just only have the F, they have the D, the A, the V, okay, and the density C, and the viscosity D. Okay, so we just put the using the SI unit. Okay, so use the SI unit. So we use the SI unit as the F. The F is the force here. So SI unit. So you just look back again at the force. Okay, so the SI unit, the force here, there's no force under M here. Okay, ML. You use the MLT. Right, okay. Force is, okay, so SI unit, so that MLT negative 2. Okay, FLT negative 2. Okay. Okay, so and SI unit. Okay, so this is the US unit. Okay, so this is the US unit. Okay, so you just, this is US unit, this is SI unit. So for the F. Okay, so for the D is L. Okay, so LA. Okay, so the velocity is L T. Okay, B. Sorry, this is B. Okay, and the density. Okay, so for the density here is, okay, you just look at the density here. Okay, so density is ml. Okay, okay, ml3. Okay, based on the C. Okay, and the kinematic viscosity, they have the kinematic viscosity. Okay, sorry, the kinematic viscosity is based on the L2D here. Okay, viscosity. So this is based on kinematic viscosity. So this is based on coefficient of viscosity. So the viscosity. Okay, so you just look at back again the viscosity here. Okay, so you just try to solve based on the SI unit. Okay, based on this one. So but look at the example here based on the US unit here. So equating the power of F, L and T on both sides. So we get the here. Okay, so for the F here, so this is only F is the one, no L and no T, so that's why the 0 here. Okay, for left side here. Okay, now look at the right side here based on this part here. Okay, so at the F, so at the A is no F. Okay, so just only F at the C here. Okay, at C, so the F is 1, so that's 1 C, and also the at D is 1 F, also 1, so 1D here. Okay, so now look at the L. So L only have the A here, so the A 1A, and at B is also 1L, so 1L is plus B, and at this one at C is 1L also, so the negative 4L. Okay, so negative 4L, so negative 4C here. Okay, and also as this also negative 2D, so that is negative 2D. Okay, and look at the T. Okay, at the T there's only have at the B here, so negative 1B. Okay, and also the plus 2C and plus 1D. Okay, so you just calculate again. So you calculate based on this is US unit. Okay, so you just calculate here. Okay, 2C and the D is T in 1. Okay. Okay, so you get the C is equal from 1 here. Okay, from 1 here. So the from 1 here. So you get the C plus D. So you get the C is equal to 1 minus by D. Okay, from 3 here. So from 3 here at this one. Okay, so you get the from 3 here. So you get the B is equal to. So you get this as a 1. Okay, so you get it as a 2. Okay, and then this is you get as the 3. Okay, after you solve this here equation, because this is F5, okay, they have 5 variables. So if you have 5 variables, so you must use that the one of the power dimension here must is in terms of D. Okay, so you just get in terms of D set. That's why we get the F is equal to K times by the D. The A is the 2 minus D, and the velocity is 2 minus by D also, and the density 1 minus by D, and the viscosity. So you get this equation, and then lastly you get this equation. So if you just stop at this part, it's okay. Okay, for this calculation for US unit. Okay, so now you look using the SI unit. Okay, try to solve based on SI unit. Okay, so now look at the theorem pi Buckingham here. Okay, theorem pi Buckingham here, when a large number of variables are involved, the large number of variables are involved, so Rayleigh method becomes lengthy, so we cannot use the Rayleigh method, so we use the theorem pi Buckingham. In such circumstance, the Buckingham method is used. Okay, this method expresses the variable related to a dimensional homogeneous equation. Okay, based on this formula, x1 is equal to f, x2, x3, x until xn. Okay, where the dimension at each section is the same. Okay, now we look at the Buckingham pi theorem can also be expressed in terms of pi as known in on the right here. Okay, based on the pi here. Okay, the procedure is count the number of variable n, then count the number of dimension m, calculate the number of pi in terms of n minus by m. Okay, select repeating variable. So repeating variable is given. Okay, so no need to worry. So multiply repeating variable, return to variable powers by each non-repeating variables to form n minus by m dimensional terms. Okay, solve for the unknown powers of the repeating variable in each pi term. Okay, so where m is the primary dimension, n is dimensional variables such as velocity, discharge, and density, and k is the reduction. Okay, actually k is no based on the reduction. K is based on the reduction. Okay, so look at the example. This is the same. The same question based on example 6.3. Okay, actually the same example of 6.3, but this is using the Rayleigh method. So we use the pi Buckingham method. Okay, so the variable is drag force. Okay, is acted on such a sphere as it moves through a viscous fluid. Certainly parameters involve diameter, velocity, dynamic viscosity, and density of fluid. Okay, express dimensional equation by pi Buckingham method. So in final, the question is based directly mentioned here. Okay, express dimensional equation by Rayleigh method or by pi Buckingham method. So in questions they must mention what method that you must do. Okay, so now you see this example 6.4. This is based on pi Buckingham method. So we use the pi Buckingham method. So the variable that involved in this calculation is force, drag force, Q1. This is a functional. Okay, F is as the constant. Okay, so D diameter, velocity, viscosity, dynamic viscosity, and the density. So they have 1, 2, 3, 4, 5. So the N is 5 variable. N is the 5 variable that involved. Okay, so the N. Okay, so the N is 5. Okay, so where FD is dependent variable. So the FD is dependent variable. Density, velocity, viscosity, and density independent variable. So the left side, so we call the dependent variable, and the right side here we call is independent variable. Okay, just remember that the left side here dependent variable and the right side here is independent variable. Okay, so choose dimensional system based on MLT theta or F. This is US base SI unit. So this example we use the SI unit. So and list the dimension of each variable and then find M. Okay, so this is based on the FD is FD. Okay, the dimensional analysis is the unit for the A is MLT here. Okay, FD is based on this functional of the D diameter is based on the length. Okay, this is based on diameter, velocity, kinematic viscosity, and the density. Okay, so actually this diameter for the length, velocity is L over T, and the MLT here. Okay, and also the density here. Okay, so this is the using the SI unit. Okay, so we know that the M is equal to def M, L, and T. There's no theta here, so the theta is 0. So we just use the 1, 2, 3. So that's why the M is base 3. Okay, just only M, L, and T. Okay, so the M is 3. So find K. So find K is usually equal to M. Okay, so K is usually equal to M. So we use the K is at the M. So which is cannot exceed but really less than M. So then find N minus K. So actually N. So K is equal to M. So this is based on the N minus by M. Okay, N minus by M. So we know that N is 5. M is 3, so we get the 2. Okay, so we get the 2. 2 is actually base for the pi. Okay, so we can write F is pi 1 and pi 2 based on the pi 1 and pi 2. Okay, So choose repeating variable which is 3 same as k. So same as k actually same as m. Okay, so as same as m, so they have m, l, and t. Okay, so they have m, they have also the L and also the LT here. Okay, so must have the M, LT. So we just choose as the diameter, velocity, and the density. Okay, so actually notes number of repeating variable must same with number of fundamental dimension or M. Okay, and choose from independent variable. In this example, choose 3. Okay, to choose this variable must relate to mass, geometry, and kinematic. Okay, so make sure that all the fundamental dimension M, L, and T is included at least in one variable. Okay, so don't worry, usually repeating variable will be given in the exam. Okay, so don't worry. So repeating variable will be given in your final. Okay, so no need to worry. So now we know that the repeating variable is the density, diameter, and also the velocity. So from pi group, so we have pi to pi. Okay, so this is pi 1, this is pi 2. Okay, for pi 1 and pi 2, so we just using this is the repeating variable. Okay, so repeating variable, so this is repeating variable. Okay, for the repeating variable, so based on the pi 1, so we can also use the repeating variable. So you can also put the velocity here A1. Okay, you put the D as B1 or the density as the C1, and the FD is at this pi 1 is okay, you can put. Okay, but you must mention that this is repeating variable, is must repeat again. Okay, so you must repeat again and the pi 2. Okay, so you must repeat again in pi 2, so you must A2. Okay, D B2 and the density C2, and use the dynamic viscosity. Okay, so this FD and also dynamic viscosity you can put in pi 1 or you can put in pi 2. Okay, meanwhile the velocity, diameter, and the density is repeating variable, so you must repeat again in this pi 2. Okay, so you can put. Okay. So I equate the exponent on both sides, solve each and from dimensionless group. So since the pi's are dimensionless, so we can replace with M O L O T O in pi 1. Okay, in pi 1. Okay, so in pi 1. So pi 1, so we put here. Okay, so look here. So pi 1, so we just use the pi 1 here. Okay, pi 1. Okay, so you just put here. Okay, so pi 1, so in this example, we use pi 1 is equal to density A1, dB1, VC1, and here. Okay, so actually the pi 1 is we use the density A1, okay, diameter B1, the velocity C1 times by the dynamic viscosity. Okay, so we put based on the this is right, so this is left side. Okay, so left side here. Okay, we put as the see here. Okay, and okay, and the right side here, so we put here. Okay, so we just put the pi 1 is mentioned as M naught, L naught, and T naught here, and put the density here based on the SI unit. M L T squared A1, okay, D is L B1, and velocity is L over T C1, and the dynamic viscosity is M over L T here. Okay, so now we put here M actually is for M, L, and T. So we know that is M0, L0, T0. Okay, actually M0, L0, T0. So in this case, for pi Buckingham method, okay, so we just assume that M0, L0, and T0. So you put the 0 here. Okay, so this is pi Buckingham method. So now we look at the AM here. So at this A here, there's the M. So M, the one here, so they have Okay, 1 times by the A1. So M is the 1 here. Okay, A1 and also the M here. Okay, they have the M here and also the M here for M. Okay, so now look at for L. They have the L here and also the L here and also L here and also L here. Okay, so they have the L here, so they have negative. This is negative 3A. So that's we get the negative 3A. And this is 1B. So we plus the 1B and also the plus the 1C1 and also the is negative 1. So they have negative 1. Okay, so we get this is S1. So we get this is S2 equation. And at the T here, so we get the T, only the T here and also the T here. Okay, so the T have negative C1, so have the negative 1 C1. Okay, and also the negative 1. Okay, so we get the 3 here. Okay, so now you solve this here. You solve as A1, so you get the negative 1. Okay, and you solve this here as C1, so you get the negative 1. Okay, so after you get the A1 and C1, just put here in the 1 here, so you get the B1. Okay, so B1, so you get the B1 is negative, the, okay, 3A1 plus C1, okay, C1, so B1 here. Okay, you solve. Okay, you solve the B here as the B1. So you get the B1 here. So you get the 3A1 is negative 1. This is negative. You just put the positive here. Okay, you get the positive 3A1 is negative 1. Okay, and the negative C1 is also 1 here. And you get the plus 1. So you get the negative 3 plus 3. So 2 plus 2. So you get the negative 1. Okay, so you get the A1, B1, C1 is this value. Okay, so you get this value. And then you just put again in the pi here. Okay, so you put again in the pi here. So you get from this one. So you get the pi 1 is negative 1. D is negative 1 also. And this is also negative 1. So you get all this negative 1. Okay, so you get the pi 1 is here. Okay, so you get the pi 1, or you can also put here as the viscosity. There's a density because it's negative 1, so it's put at the bottom here. And okay, so we insert A1, B1, C1 into the equation. So now you repeat step 6 to 7 for pi 2. Okay, so rearrange the pi group. So now you repeat again based on the from 6 here, okay, until to 7 again here to get the pi 2. So now you look at the pi 2. Okay, you repeat again based on the pi 2 here is density A2, okay, and the B2, okay, and the velocity C2, and you get the FD. Okay, so you just do again based on the pi 2. Okay, you calculate again as here. Okay, as here. Okay, as this calculation here, you just calculate again based on pi 2. Okay, so pi 2, so you get the P here is also as the here. Okay, MLTA2 L C B2 C2, and you just get again the A2 B1 B2 and C1 2. Okay, so you get the A2, you get the B2, and you get the C2. Okay, you just calculate again. Okay, so you just calculate again based on the calculation here. Okay, so you just calculate again as the here, and you get the A2, B2, and C2 until you get the pi 2 as this formula. Okay, so now you rearrange based on pi 1 and the pi 2, so you get this last formula here. Okay, so this is pi 1 is equal to the functional of pi 2. Okay. Okay, so you solve that, you get the A2, B2, and C3 based on this calculation. Okay, so this calculation is based on the pi 1. Okay, so you repeat again this calculation based on to A2, B2, C2, and so on until you get the A2, B2, and C2. Okay, based on this formula until you get the last formula for pi 2 is this one. Okay. Now we look at example here, derive an expression for the flow rate per unit width Q, okay, over the spillway shown in figure. So the variables that affect Q are the H, the acceleration of gravity G, and the spillway height P. Okay, to get the P here. Okay, so the variable is involved in this calculation is based on the Q here. Okay, based on the Q, flow rate per unit width Q. Okay, the variable that affects the head, the acceleration of G, and also the P. Okay, so the variable is list the influence factor and count. So they have the Q, functional of H, functional of the P, and the G. So the N is 4. Okay, 1, 2, 3, 4. So the N is 4. Okay, choose dimensional system. Okay, MLT in this least dimension of each variable and 5m. Okay, based on from this calculation, based on this formula, you choose the MLT here. So this is the unit, the DA unit. So this is the H height, and the P also the L, and the G here. Okay, so they just only have M, L, and T. So they just only have L and T. Okay, no M, so no M, no theta. So they just only have L and T. Okay, L and T. So they have M is 2. Okay, so M minus, so N minus by M. So M minus by, so M is 2. So N minus by M is 2. So we can write the function, the pi 1 and pi 2 is 2. Okay, so we get the pi 1 and pi 2. Okay, so pi 1 and pi 2. Okay, so pi 1 for this, so pi 1 is using the repeating variable is GH. Okay, so GH is the repeating variable. Okay, so we put the G, A1, H, B1, Q, and pi 2 is G, A2, H, B2, and P. Okay, because based on the Q, functional of, okay, G, H, and P. Okay, so G and H is repeating variable. Okay, so the repeating variable here. Okay, that's why you must put the pi 1 is G, A1, B1, Q, pi 2, G, A2, H, B2, P. So this is the pi 1 and pi 2. So now you calculate the pi 1 based on this formula. Okay, they just only have L, T. Okay, for L and also T. So L is 0, T also 0. So we just put here. Okay, base until you get the, you solve. Okay, this is 1, this is 2. Okay, so you get and solve, and then you solving for A1 and B1. So you get the A1 is negative 1 over 2, and B is also negative 3 over 2. Okay, so you get the pi 1 is, okay, Q, okay, G based on GH3. Okay, actually it's based on the L1 here, 1. Okay, A is a negative 1 here. So until you get the, actually for the here, okay, pi 1. So you get the pi 1 is G A1. Okay, G A1. So you get the G A1, GH. Okay, GH, GH, B1 and P, Q, okay, and the Q until you get the Q here, okay. So until you get the pi 1 is based on the here, put the A here, okay, you get the A, you put the A here as the A1, B1. So A1 is negative 2, this is negative 3, 2. Okay, so you get the G, okay, half and the 3 here and the Q here. So you get the formula here. And then you solve the pi 2 here, okay. You solve for pi 2 here based on this formula, and then you get the value of A2 and also the B2. So now you just put the pi 2. Okay, actually pi 2 is G, A2 is 0, okay, and H, you get the H is negative 1 and the P, okay. So until you get this one, okay, so G0 is 1, okay, so you get the P and H1 here. Then you get the pi 1 is functional with the pi 2, okay. So you get this formula, okay. So you derive that the Buckingham method, okay. So until you get this also, okay. So you stop at this part, it's okay, or you can put until you get this one, okay. So now we look at the similitude, okay. For the similitude, actually it's based on the theory, more on theory. In hydraulic and aeronautical engineering, valuable results are obtained at relative small cost, okay, by performing tests on small scale model of full size prototypes, or system is called prototype. So similarity laws help us to interpret the result of model studies. Okay, the relation between model and prototype is called classified into three: geometric similarity, kinematic similarity, okay, and dynamic similarity. This is more on theory, okay. So in case in your final ask you to explain what is geometric similarity, what is kinematic similarity, and dynamic similarity, so you can explain based on the similarity laws, okay. Similarity laws based on the similitude, okay. So they have the scale ratio, okay. So model is similar with object or structure required in certain scale ratio, tested in laboratory and similar in real phenomenon. So not necessary it's smaller than prototype, okay. Model is not necessary because it's smaller than prototype, okay. For prototype is object or actual structure tested in actual phenomenon, example as structure in open channel or ship, okay. So prototype is the object or actual structure. So maybe in your final ask you what is prototype, define the prototype and model. So you can define based on prototype and model, okay. So advantages of similarity, so its performance of object can be predicted, economic and easy to build, where design of model can be done many times until reach a certain values, and non-functional structure also can be measured, such as a dam. Okay, so geometric similarity. So the prototype and model have identical shape but differ only in size. So ratio corresponding length in prototype and model shows as LP over LM is equal to LR. Okay, so area AP over AM is equal to LP squared over LM squared here. So you get the LR. Okay, so this is for the using the geometric similarity. Okay, volume is a volume prototype divided by volume model. So M is model, okay. To get the length of the geometry similarity, so length of prototype divided by L model, so you get the LR, okay. Area of prototype divided by area of model, so we know that the length prototype, okay, power of 2, length of model power 2, so we get the LR2 here, okay, and volume here. So this is actually based on the unit, okay. Actually this is based on the unit, okay. So now we look at the kinematic similarity. So kinematic similarity, in addition to geometric similarity, ratio of velocities at all corresponding points in flow are the same. So involve length and time. So this is kinematic similarity based on involved length and time. So time, TP divided by TM. T for time for prototype divided by time for model, so we get the TR. Okay, so TR is time for kinematic similarity. Okay, so velocity, so VP over VM. So VP, we know that the VP is the here. Okay, VP and VM. Okay, so LP over TP here. Okay, based on the unit here. Okay, for volume velocity, LP over TP here, LM over TM here. So we know that LP over LM, okay, TP over TM here. So we get the LR over TR here. Okay, so actually this is based on length and time for kinematic similarity. So for acceleration, so we know that AP over AM. So AP, LP over T squared, okay, LM over TM squared here, and then you get the LP over LM here, and TP2 over here, okay. So and then you get the LR over TR squared here, okay, and the discharge also, okay, L3 over T, okay, because it's based on the unit, okay, length cubic per time, okay, length cubic per time. So we just put here. So this is kinematic similarity. For dynamic similarity, two systems have dynamic similarity if in addition to dynamic similarity, corresponding force are in the same ratio in both. Okay, so the force scale ratio is Fp over Fm. So if they use the forces, this is dynamic similarity because they're using the F here. Okay, so forces that may act on the fluid elements include those to gravity, Fg, pressure, Fp, viscosity, Fv, and elasticity and surface tension. So this is based on the F, is the core dynamic similarity. Okay, so these forces can be expressed in the simple terms inertia, or F1 is equal to ma. Okay, using the density times by the length power of 4. Okay, and the second, actually this is based on the unit. Okay, based on the mass is based on the density and so on. Okay, and the pressure here. Okay, so no need to worry because this is just for your theory. Okay, and then the viscosity, elasticity, and surface tension is based on the here. Okay, actually this formula is given in your final. Okay, if they have the calculation based on the dynamic similarity. Okay, so actually this is dynamic similarity. If you see this formula in your final question, so let's use this equation and just solve. Okay, based on the, actually this is for dynamic. Okay, actually dynamic similarity is based on force. Okay, for kinematic, length and time. Okay, so the dynamic based on the forces, kinematic is based on length and time, and geometric just only length. Okay, so that's the difference based on geometric, kinematic, and dynamic similarity. Okay, so now the non-dimensional parameters, the important parameters are Reynolds and Froude number. Okay, so this is non-dimensional parameters based on, we learn this Reynolds number and Froude number from the start, okay, topic 1 until chapter 6. So you learn number based on the advanced, okay, the fluid mechanics based on the advanced. So we just learn the Reynolds number and Froude number. Okay, so this is the given to you. Okay, this table is for model and prototype. Actually this is the DA unit. So this is DA. Okay, DA that we have learned in the previous, okay, the previous topic here. Okay, previous slide in chapter 6 here. Okay, and this is the DA, and this is based on the Reynolds and also the Froude. Okay, so Reynolds number are used when there is a dominant action of viscous force or ratio of inertial forces to viscous force. Okay, example, completely submerged flow in ship, complete enclosed flow through a pipe. So all these example we have learned in, okay, the previous topic. Okay, so viscous flow and settling particle in fluid, flow in flow meters in pipe. This is orifice meter and so on. So we have learned the Reynolds number, okay, in the previous chapter. Okay, so Reynolds number, based on the Reynolds number here, so we get the LVP here. Okay, actually this is based on the Reynolds number. Dynamic similarity achieved when LV over viscosity here is equal to Reynolds number. Model is equal to Reynolds number. prototype. So we get the Reynolds number VL divided by the viscosity for model is equal to VL viscosity prototype. So the prototype and model is equal based on the similarity. Okay, so if the Reynolds number of a model and prototypes are the same, find the expression. So this is just expression based on the ratio of VR, TR, and AR is the Reynolds. Okay, velocity for Reynolds, okay, is equal V for prototype divided by V for model. Okay, so you just put the here until you get the VR and AR. Okay, actually this is based on using the unit. Okay, just convert to unit and so on. Okay, based on the prototype and model. Okay, you just study for this example. Okay, so just study here. Okay, and also the example here based on the model and the here. Okay, so no need to worry about this one. You just study here until you get the value. Okay, so and the Froude number used when there is dominant action of gravity forces or ratio of inertial forces to gravity force. Example with action as in breakwater, ship, free surface flow, hydraulic structure, such as spillway, weirs, notch. Okay, force on the bridge, piers, and offshore structure. So this is based on Froude number. So Froude number using this formula here, Froude number is equal to velocity divided by GL here. Okay, based on the dynamic similarity achieved when we use this is based on the Froude number model and also the Froude number for prototype. So this is the basic assumption that you must know. Okay, also the same as the Reynolds number. Okay, so based on the Froude law, you find the ratio of velocity, discharge force, work and power in terms of length scale. Okay, so based on the Froude number formula, so you just put as the prototype and equal to Froude number based on the model here. Okay, so you can use here. Okay, so LP over LM is equal to LR and P. That's TP prototype and that's TP model. So we get the sorry, Froude number here. Actually, FR is Froude number. Okay, velocity ratio. Velocity ratio here based on just put here, and you just get the value here. Okay, just put using the DA, and then so on to get the force ratio. Okay, the force ratio here and work ratio, just put the value and this value. So, and you get the value. Okay, that's all for topic 9, and this is the last topic that you have learned in this semester. So that's all. Thank you. If you have any question, you can ask me in the group, and also you can just direct PM to me. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.